All right, I think we're live then. Happy Friday, everyone. And welcome to another exciting episode of Get Your Tech On. And this is our Back to Basics series. I'm your host, Brady Volpe, and I'm thrilled to be joined today again by the legendary Ron Hranac, a 50-year veteran in the cable industry and a fellow member of the SCTE. Today, we're going to be delving into the fascinating topic of carrier-to-noise ratio, or CNR, and learning the basics of this essential concept. We're going to be talking about thermal to noise, the perfect amplifier, to noise figure, and practical CNR measurements. We'll cover everything you need to know about CNR and its applications. So grab a pen and paper and get ready to take some notes, because this is going to be a deep dive into the world of carrier to noise ratio, and there may be a quiz at the end. So Ron is so well known in the industry, he doesn't need an intro, but please check out his full bio in the description below. And let's introduce the epic Ron Hranac. Ron, it is so good to see you again.
Good to see you, Brady, and thanks for the kind words. Much appreciated. The check will be in the mail for all the things you just said. Now, this should be, I think, a good presentation today. It continues the line of discussions that we've been having in the last few sessions, and hopefully those who are tuned in today and also those who will be watching the recording later have had a chance to review the earlier sessions on the decibel and putting the decibel to work and signal level, because all of those serve as a good foundation for what we're talking about today. Good old carrier to noise ratio. And hopefully when this is done, people will have a better understanding of what it is and why it's important.
Absolutely. So let's go ahead and get started, Ron. And those previous videos have been great building blocks, so we'll make sure those links are also in the description below. Ron, as you go ahead and get your PowerPoint up and running, I'd like to ask everyone, please do subscribe, hit the notification bell. We certainly appreciate that. And that way you get notifications when we have more of this great content coming out, particularly from Ron. So.
Whoops, I hit the wrong one. I want to hit that one.
No problem, Ron. Your presentation is up, and it's looking great.
This little box over to the right. All right, here's the title slide, Introduction to Carrier to Noise Ratio. And you see the professor there standing in front of a chalkboard, and you're thinking, uh-oh. And yes, caution, mathematics ahead.
And a quiz at the end.
Yeah, that's one of those fun things. But you really have to understand at least some of the math to get a good grasp of what the heck this carrier to noise ratio thing is all about. And all right, what is this carrier to noise ratio thing all about? Carrier to noise ratio, abbreviated CNR, and some people abbreviate it C/N. I'm using CNR throughout this presentation, but it's generally accepted to be what's called a pre-detection measurement. That means it's made in the frequency domain at RF. They're typically made using commonly available test equipment, signal level meters, spectrum analyzers, some specialized test equipment, but I think by and large, these two instruments are the ones that most people use when measuring carrier to noise ratio in their head ends or outside plant. So step one, when we talk about measuring carrier to noise ratio, is to measure the C in CNR. That's the carrier's RF signal level. The next, to measure the N in CNR, which is the noise's signal level. Now, note the point in parentheses. This is important, and we're going to talk about this a little bit more later on. Apply a noise bandwidth correction to your noise measurement if necessary. And then finally, step 3, the difference in dB between the C that you just measured and the N that you just measured. And if you had to correct the amplitude of the N to refer to a specific noise power bandwidth, then the difference between the C and the N is the carrier to noise ratio in dB. And the example you see here is about 15 dB. And you can see that right on the spectrum analyzer. And you might say, well, do I actually have to measure the C and then measure the N to get an idea? And the answer, of course, is it depends.
Well, that was great, Ron. Now we understand CNR. Thank you so much. Can't we just stop there? Can't we stop? Yeah, quick questions.
Yeah.
So it gets deeper, though, doesn't it? I mean, so I think sometimes we think that's it for CNR. But
Well, yeah,
I
you
think you're
can't.
going. I think you have more content now, don't you?
There is more content, and you can't just look at the display and say, okay, that's the CNR, because it might be, and it might not be. So let's start with carrier to noise ratio measurements that many who have been in the industry a long time are probably very familiar with, and that's on analog TV channels. So in this case, the CNR is described as the difference in decibels, or good old dB, between the amplitude of the TV channel's visual carrier, and that's the tall one here you see, um, and then the amplitude of the system noise in a defined or specified bandwidth. Interestingly, if you check Part 76 of the FCC rules, it says that the noise measurement has to be done in a 4 megahertz bandwidth or corrected to a 4 megahertz bandwidth. Um, so if you look at this spectrum analyzer screenshot, I've got dotted lines there that correspond to the approximate amplitude of the visual carrier and the approximate amplitude of the noise floor. You look at this and you say, okay, that looks about 40 dB carrier to noise ratio, give or take a couple dB. And of course, the question then is it? We'll talk about this a little bit more later on. Now, for SC QAM channels, or single carrier QAM channels, CNR is the difference in dB between the amplitude of the haystack and the amplitude of the system noise. Good news here is you don't need to do any bandwidth correction on the noise floor because you're measuring a noise-like digital signal and noise-like noise. The same's true for OFDM signals. You measure from the top of the haystack. I don't have an OFDM signal showing on the screen here, but you measure from the top of the haystack. An important point when measuring an OFDM signal, the height of it on a spectrum analyzer, don't measure the top of the pilots. They're typically boosted 6 dB above the top of the data subcarriers. You want to measure from the data subcarriers. So basically the haystack, but not from the top of those pilots. And then, of course, you measure the noise as before, and that gives you your carrier to noise ratio.
Now, Ron, I have a quick question for you. I see your line is kind of in the middle of that SC QAM channel. Does it matter if you're at the top of the SC QAM channel, or it's kind of fuzzy, or at the bottom of the SC QAM?
I like putting it about in the middle, just as long as you're consistent in doing it for the SC QAM signal and the noise floor. You should more or less get the same answer if you put it at the top of both. I like to put it in the middle because that to me just is a little easier to do, and I think it just helps simplify things.
Okay, thank you.
Yeah, that's more user preference. If you wanted to get really picky about it, you could use the marker noise method in the spectrum analyzer and measure the noise power of the SC QAM signal in a 1 hertz bandwidth and the noise power of the noise floor in a 1 hertz bandwidth. There's some adjustments you have to make to the analyzer settings to do that, but that's the most accurate way if you really want to get real accurate. But to get a ballpark carrier to noise ratio like you see here, you look at this and you say, okay, that looks like it's 25, 26 dB, give or take. And I'll ask this question again. Is it? Remember, you don't have to do a noise bandwidth correction when measuring the carrier to noise ratio of SC QAM signals, but is this a legitimate carrier to noise ratio measurement? We'll talk about this more a little bit later on too. Oh, and then we get into the math. And no, I'm not going to make people do homework here. This description here on the slide is from the book Modern Cable Television Technology. And it says the carrier to noise ratio, and they use C/N, is defined as follows with this equation. C/N in dB is identical to 10 times the logarithm of a small c over a small n. And in this definition, the lowercase c and n are the scalar power levels of the carrier and the noise, not the decibel value. So we'll go down below to the footnote here, and here the scalar quantities are in units of watts. And we talked about watts versus dB early on in this series. So if you're a little confused about that, go back and take a look at those earlier sessions for an understanding of that. The logarithmic quantities, that is what we would get here, this C/N and dB is in units of dBmV. So we can do an example here. So we can insert a value in watts. So this 0.00133333333 watt divided by 0.000000042.164 watt. Run through the math. You divide this, take the base 10 logarithm of that fraction, multiply by 10, you get 45 dB. And the example I used is the wattage that you see here is 50 dBmV and 5 dBmV respectively. And you look at this and say, is that a typo on the equal sign? That's not an equal sign. It means is identical to. That is a math sign. It's a real one. But you see why when you look at those values in watts, we use the decibel rather than the actual scalar values, because those are such tiny numbers to try to deal with. So not very convenient. Much more convenient to deal in the world of decibels. But this is part of that math.
So back to the decibel and also math. So I mean, if I don't like math, do I really have to learn this math, Ron? Is this important to CNR?
I think it is. If nothing else, the basic relationships we talked about in putting the decibel to work are one of our previous sessions. Did talk about the relationships. What happens when you change the value in decibels by, say, 10 dB or 20 dB or 3 dB? What does that do to the power, and vice versa? You at least need to be familiar with those, and I think you'll see why a little later on. Now, continuing with definitions, just to make sure everybody is clear on this, our math document that was created by SCTE's Network Operations Subcommittee Working Group 1 and is called SCTE 270 2021 R1 Mathematics of Cable, that good old 425-page document on math, is such a great reference. It has a definition for carrier to noise ratio, and it says the ratio of carrier signal power to the thermal noise power in a specified bandwidth as measured on RF spectrum analyzers and similar equipment, and so on. And you look at the graphic on the right, and you can see that we've got a CW carrier with an amplitude of 32 dBmV, noise levels minus 31 dBmV, and the difference in dB between the carrier level in dBmV and the signal level of the noise in a specified bandwidth in dBmV is CNR. So far, so good. Oh, then we get into thermal noise. What the heck is thermal noise? The graphic in the upper right of the slide here shows what thermal noise looks like in the time domain. That's what it would look like on an oscilloscope.
Isn't that noise from your hairdryer? Thermal noise?
This is not noise from a hairdryer. That's more being impulsive. This would be noise from, say, a resistor or an impedance.
How can a resistor make noise?
Oh, that's tricky. And let me read through this definition here, and then we'll get back to that. There's a really cool application note that HP published way back when. And it's I think it's been updated over time at Agilent and Keysight. But it's Fundamentals of RF and Microwave Noise Figure Measurement, application note 57-1. Some of this text came from that. And according to that note on noise figure measurement, thermal noise is defined as the fluctuating voltage across a resistance due to the random motion of free charge caused by thermal agitation. You go, what? Here's the translation. Atomic particles in a resistor or impedance jiggle around more at higher temperatures and less at lower temperatures. That atomic level jiggling creates measurable noise. And Brady, back to your question, how on earth can a resistor sitting on the table at room temperature generate thermal noise? It involves a little bit of physics, and it involves kinetic energy and ionized particles, so think electrons and ions, when connected via a suitable conduction path, such as the metallic leads on a resistor, can convert that vibration to a measurable thermal noise. The application note actually does a pretty good job of describing the physics in a few sentences, but we won't go there because we don't want people to fall asleep before we get to the end of today's presentation.
Yeah, I think that would put them to sleep. So that is pretty interesting. I mean,
it's interesting to think about that a simple resistor or an impedance can generate thermal noise, and yeah, it can. The warmer it is, the more noise that resistor generates. The colder it is, the less it generates. But you can measure it.
Indeed. In just a moment, Ron, we'll just head over to the chat room. Thanks for joining in, folks, in the chat room. And Peter Vittman makes a comment back to the topics when we were talking about just kind of that noise on the SC-QAM channel. So he's talking about, will the amplitude average option in the spectrum analyzer for SC-QAM also be a good idea to get more accurate CNR measurements?
You could, I suppose. I think if you want real accurate measurements, if it were me, I'd use the power per hertz, the marker noise function. That to me is probably the best way to do it.
The most accurate way.
If you want real accuracy, I'd go with the marker noise measurement. Refer to the instructions of your spectrum analyzer, because you may need to center the QAM haystack on your screen and then set the frequency per division control such that SC QAM signal occupies a good chunk of the display, and then get the marker right near the center of that, or off a little bit, but close to the center, and then let it do its 1 hertz noise measurement, and then do the same thing to a chunk of spectrum with no signals in it other than the thermal noise floor, and do the same thing. But check the instructions of the spectrum for the spectrum analyzer to see how you need to configure the analyzer to do a marker noise measurement. That, in my opinion, will probably give you the most accurate measurement of a noise-like signal and the noise.
Great. Thanks for the question, Peter.
Yeah, that's a good question. All right, here's the gnarly part. This formula is from the application note that I just referenced, and it says the probability distribution of the voltage is Gaussian with the mean square voltage. Basically, this is saying that we're talking about additive white Gaussian noise, and I am not going to dig into the math that you see on the screen. I simply wanted to present this just to point out that, yeah, there is some math that goes along with this. The kind of math we do want to pay attention to, though, is right here. That available noise power can be expressed in joules per second, which is watts, using the formula, and this has been around forever, P equals KTB, where P is the power in watts, K is Boltzmann's constant, the T is the temperature in Kelvin, and B is bandwidth in hertz. And notice it's not degrees Kelvin. There's no degree sign with Kelvin, because that would be redundant if you tried to do that. It is simply Kelvin, lowercase k on the word, uppercase K for the symbol. But that comes from the International System of Units, for those who are wondering why. And then continuing on, if we want to get the thermal noise power into the world that we're familiar with, good old dBmV, or dBmuV if you happen to be in Europe, but we're going to give the example here in dBmV. You start with a variation of that gnarly formula a couple slides back. Yes, really, this is a variation of that formula. From that formula, you can derive the following formula for calculating the open circuit noise voltage coming from a resistor or an impedance. And here's the formula. So we're going to use this E subscript N equals the square root of 4 times KTB R. And then we'll define what all these things mean. So let's use an example. Let's say, let me get this little box just a wee bit more out of the way. Let's say we've got a 75 ohm resistor laying on the table. We're going to hook up a special meter to it and measure the voltage coming out of that. But first we'll calculate it and see what it is. And we'll assume that the impedance is 75 ohms, so that's R, and a 4 megahertz bandwidth, so that is 4 million hertz. We know Boltzmann's constant, 1.38 times 10 to the minus 23rd, and we got 4 times Boltzmann's constant times temperature. This is room temperature in Kelvin, 293.15 Kelvin, times the bandwidth is 4 million hertz, or 4 megahertz, times the impedance or resistance, 75 ohms. Multiply all that stuff together, gives us 4.85 times 10 to the minus 12. Take the square root. We get 2.2 times 10 to the minus 6 volt, or 2.2 microvolts. And there it is. And of course, this is at room temperature, 68 degrees Fahrenheit. I need to point out that some people, whoops, why didn't I get my little box here?
The missing piece.
Oh, there it is on the next
There it is. Okay.
Yeah, we'll come back to that in a second. I was thinking it was on this slide. So we've got the open circuit noise voltage, about 2.2 microvolts at room temperature. So in order to be practical, of course, we have to terminate that noise source, the resistor, by an equal value resistance or impedance. So let's say we connect that 75 ohm resistor to the input of a 75 ohm impedance amplifier. So the thermal noise then is going to be the EN divided by 2. So instead of 2.2 microvolts, it's 1.1 microvolts, more or less. And then once we have that number, we convert that to dBmV with the formula 20 times the base 10 logarithm of the value in microvolts, which is 1.1016535 microvolts, divided by 1,000, and that gives us minus 59.16 dBmV. In other words, 1.1 microvolt, in the example you see here in the graphic in the lower right screen, equals minus 59.16 dBmV. There's the part that I was looking for. I forgot that I put it on this slide. It's important to note that some people prefer to calculate thermal noise in a 4 megahertz bandwidth at what's called a standard noise temperature, T0. And that's usually 290 Kelvin or 62.3 degrees Fahrenheit. So that gives us a very slightly different dBmV reading than at room temperature of 68 degrees. So at 62 degrees, 62 and change degrees, it's minus 59.21 dBmV. So we've got minus 59.16 dBmV room temperature, minus 59.21 dBmV for the so-called standard noise temperature. And I've seen references to both or use both. In the examples that I'm going to go through here in just a little bit, we'll use the room temperature value since that's been commonly used by the cable industry for a long time. But if you want to use the standard noise temperature, you're free to do so. Just keep in mind that that it will affect your answer a little bit, but it's just a little bit.
Now, in a perfect world, this would be your thermal noise floor if you had a perfect amplifier that had a 75 ohm output impedance terminated to a perfect 75 ohm terminator, correct? That's basically how we would interpret this.
It is, but this number that we've just calculated, the minus 59.16 dBmV, we're going to use that with a perfect amplifier and a real world amplifier.
Okay.
That's the important point. So it's going to really be applicable to either one or both. And of course, that takes us to how to calculate the carrier to noise ratio of just, say, an amplifier sitting on the bench by itself. And this would be, a line extender, trunk amp, or whatever. And if you want to calculate the carrier to noise ratio first of this amplifier by itself, now you're sitting here thinking, why is Ron talking about all this stuff? Isn't this something the vendors do? And the answer is yes, they do, but it's good to understand how they come up with a carrier to noise ratio spec for their equipment, because they'll calculate it first and then they'll measure it, make sure that the measurement corresponds closely to the calculated value. That part is pretty critical. But understanding where this comes from will help, I think, put all of this into context, particularly if you get out into the field and you're measuring carrier to noise ratio and say, all right, why or how? And this is the why and the how. So let's take that line extender amplifier. We'll just assume it's a line extender sitting on the test bench. We want to calculate the carrier to noise ratio of that amp. And then we can measure it afterwards to see if it really is that. So the carrier to noise ratio of an individual amplifier equals NT, that's the thermal noise floor, but that's the value in dBmV. But here, to give us a positive number for CNR, we're going to just leave the minus sign off that just for this calculation. Minus NF, which is the noise figure of the amplifier, that's in a value in dB. And then we're going to add to that I, which is the RF input level to that amplifier in dBmV. So that part, pretty straightforward. And I do need to point out a good caveat right here. The formula assumes that the plug-in attenuator and the plug-in equalizer are 0 dB values. If they're not, then you need to change the math in your formula. And the best way is to change it in the noise figure number. So let's take an example. Let's say that the amplifier's actual noise figure is 10 dB. And we'll say we've got a 0 dB attenuator on the input to this amplifier, but we plug in an equalizer, and the equalizer's insertion loss is a dB. So in this case, to account for that, we would change the noise figure value that we use in the formula from 10 dB to 11 dB. We just add the insertion loss of that equalizer to the noise figure number. That's all. But if
the amplifier got a little bit noisier by 1 dB.
It did. Yep.
Just because of that equalizer. And I think that's actually something important for people to understand is they have to realize as technicians. And I think that's why you're talking about this background, Ron, is like we just arbitrarily start plugging EQs in and pads in, and we don't understand the impact that's going to have on how that impacts the CNR of the amplifier.
Well, yeah, you plug in too much attenuation. What's that going to do to your
noise
output?
floor goes down. Your CNR gets worse.
Noise floor, yeah, the CNR gets worse. Anyway, so let's look at a block diagram here of a perfect amplifier. Of course, we know in real life these things don't exist, but let's look at, we'll start with this discussion first. So let's say we've got our minus 59 dBmV thermal noise at the input to the amplifier from our resistor. And then we'll figure out how to inject a 12 dBmV input carrier. And we'll assume that that's coming from a noiseless source, because otherwise things start to get a little messy, but we'll assume that's coming from a noiseless source. Pretend the amplifier has 20 dB of gain, so probably not unusual for an older line extender type. And of course, if the amplifier has 20 dB of gain, that means the input RF signal level, which is 12 dBmV, will be amplified by 20 dB. So at the output, we'll have 32 dBmV. That's pretty straightforward. The noise going in is minus 59 dBmV. We boost that up by 20 dB, and we got minus 39 dBmV at the output. Then you look at the CNR at the input and the output. It's the difference between the carrier level and the noise level. So we got a 71 dB CNR at the input and a 71 dB CNR at the output.
Where can I buy these amplifiers, by the way? What vendor sells these?
Yeah, these are really expensive.
super expensive.
Really expensive. They're made of unobtainium. They don't exist. That's not what really happens.
Darn.
So in the real world, and this makes it a bit more challenging. So we'll start at the input, and I've got a graphic here that represents what you might see on a spectrum analyzer. So we've got 12 dBmV input for the carrier and minus 59 dBmV input for the noise floor. So that's a 71 dB carrier to noise ratio. And then on the output of our 20 dB gain amp, the carrier level goes up 20 dB from plus 12 to plus 32. But the noise goes from minus 59 to plus or minus 31. And you say, wait a minute, shouldn't that have been minus 39? Does this mean the amplifier has special circuits that amplify the noise a different amount than it does the signal? And the answer is no.
It has those darn resistors in there.
Well, there's resistors in there, but there's other stuff. There's transistors and other things that are adding noise. So our amplifier has added noise to the noise coming into the amplifier. And of course, it adds a little bit to the signal, but the signal's high enough that it's negligible. But there's additional noise added by the amplifier circuits. Oh, so here's the block diagram again. So we've got our 71 dB CNR on the input, but the output, it's 63 dB CNR. And in this example, you can see the output CNR is worse than the input CNR by 8 dB compared to the perfect amplifier. That degradation of the CNR through the amplifier is called the amplifier's noise figure. Don't worry, we're not going to get into the how and why of noise figure. That's a pretty complicated subject, maybe suitable for another time, but there's some good material out there on the web that talks about noise figure. Good news is you don't have to worry about it. The manufacturers publish the noise figure in their spec sheets. They use very sophisticated and expensive test equipment to measure the noise figure of their amplifiers. So look on the data sheet and you'll get the noise figure there. Okay. So let's take our standalone pretend amplifier, a real world one, and let's say that the amplifier has 8 dB of noise figure. We've got a 0 dB pad and a 0 dB equalizer plugged in. 12 dBmV input. What's the carrier to noise ratio of this amplifier by itself? So we've got that 59.16 dBmV, and remember we took the minus sign off just for this formula. Minus 8, that's the noise figure, plus 12, that's the RF input level, gives us a standalone carrier to noise ratio of a little over 63 dB. So 63.16 dB is our carrier to noise ratio of one amplifier. And this is pretty straightforward. Next, we're going to connect a cascade of identical amplifiers together. And if we want to calculate the CNR of that cascade, we can use the formula here in red. So that's the carrier to noise ratio total. That's what we'll see at the end of the line is equal to the carrier to noise ratio of an individual amplifier minus 10 times the base 10 logarithm of n, where n is the number of amplifiers in cascade. So let's say we've got a cascade of 6 identical amplifiers, same operational parameters and everything on every one. So each one has 8 dB noise figure, 12 dB MV input, standalone CNR of 63 dB. And we're going to have an end-of-line CNR, going through the math, of 55.38 dB. Now, here's a point where you might ask the question, well, why do I care what the math says? I'll just go measure it. But if you go measure it, how do you know that's what it's supposed to be? If you can calculate the end-of-line CNR, you kind of have a good idea of what to expect when you go out there and actually make the measurement. You should be within probably a dB or two of what your calculated value is.
And then the CNR start to become a factor as to how long our cascades are. I mean, so you showed like six amplifiers in cascade. Is that why we want to make our cascades shorter rather than making our cascades of amplifiers longer?
Well, it depends to that, but in general, yes. The longer the cascade, the worse the CNR. So here's a question, and feel free to answer in the chat window. What happens to the end-of-line CNR if the cascade length doubles from 6 that we have here to 12 amplifiers? And we maintain the same amplifier performance parameters. So same input signal level, everything has the same gain, same noise figure, all that's the same. We'll assume 0 dB attenuator and equalizer. So everything's the same. We just doubled the cascade from 6 to 12. What happens to the CNR?
We'll leave that in the chat window. So there's about a minute delay, so we'll see what the chat comes up with that.
All right. And we'll hang out here for a second and let people chime in.
So, also, Ron, I think the other thing that reduces cascade size is the number of subscribers on a cascade, right? The longer the cascade, the more subscribers you get, the more users that you're going to be having on the network as well. So the more utilization.
That's true. Of course, if we're not concerned with that, and we'll pretend we've got some data transmission technology that can fix that, but yeah, that's a great point. I think the reality, though, is, of course, we think back to the days of tree and branch networks before we had HFC networks. I worked in a cable system back in the late 70s that had the longest trunk cascade was 67 trunk amps, and then, of course, a bridger and a couple line extenders. And I got to tell you, there was only 12 channels, thankfully, but the carrier to noise ratio at the end of 67 amps was pretty nasty.
How did you deal with that when you have really poor carrier to noise ratio on a cascade that was that deep?
We had a sweep tech who had a full-time job, and he had to sweep the plant to maintain optimum input levels, output levels, padding, and so on, to ensure that we had the best CNR we could get in that length of a cascade. What we ended up doing, and remember, this is before we had fiber available to do HFC, we put in good old Hughes AML microwave, and we broke up those cascades to, I think typically 25 amps plus or minus a few. And that improved the network reliability a bunch, and of course improved the carrier to noise ratio. But the question is, how much? But let's see what we've got from folks in the chat window.
So Peter comes in and says, blind guess, lower the CNR by 3 dB.
We lower it. Okay. Anybody else?
I think Peter's the only one that's going to. I think you're going to have to give us the answer, Ron.
Yep. The answer is it gets worse by 3 dB, actually 3.01 dB. So
Peter
instead of 55, love it. Instead of 55.38 dB carrier to noise ratio at the end of the 12th amplifier, it's going to be 53.37, if I did that math right in my head. So we'll call it 3 dB worse carrier to noise ratio.
And that's like almost back to our, what we talked about when we first introduced the decibel. It's that doubling factor. So you double it and it gets worse by 3 dB.
And if you cut it in half, it gets worse by 3.
Yeah.
Let me look there. And here we can cheat and see if we go to the third amplifier, guess what? It's 3 dB better than our end of line at 6. Yep. So if you cut the cascade down to 3 after the node, you'd have 58 instead of 55. Well,
Which
of
is
course, you'd have to take into account your carrier to noise ratio coming out of the node and so on and do a power addition. But that's coming up on how we calculate carrier to noise ratio when we've got different numbers and they're not all the same like these are.
nice.
And there it is. There's the segue. You've got different carrier to noise ratios. Let's say you have a cascade of amplifiers, but they're not identical amplifiers. Or you're calculating the combined carrier to noise ratio in the upstream. Let's say you're combining nodes back in the head end or the outputs of your upstream receivers. How do you calculate carrier to noise ratio if you've got different CNRs? And you use this formula. You notice it's got minus signs in front of these numbers to make the answer come out right. But this carrier to noise ratio total equals minus 10 times the logarithm of, and then parens, you've got all the numbers there where that subscript n at the end here would be the number of the nth carrier to noise ratio. So this is the first carrier to noise ratio, the second carrier to noise ratio, third, fourth, and whatever. And then the n is the nth carrier to noise ratio. So here's an example. Let's say that we're doing this in our system, and I know a lot of operators have moved away from this, but let's say that we've got 4 optical receivers in the head end. We take the RF output, connect them to a backwards 4-way splitter, acting like a combiner. We have these carrier to noise ratios, 32, 32, 34, and 35. What's the combined CNR here at the input to our, in this case, upstream port on the CMTS? And we use that formula on the previous slide to do that. Now, looking at the CNRs here, of course, you can never combine CNRs and get better CNR than the numbers you've got here. And in fact, if you look at this, you're always going to have a CNR, a combined CNR that is worse than your lowest value in the group that you're combining. So there's the math, and what we get when we plug in the numbers, we've got the minus 32, the 32, 34, 35, crunch the numbers, and we wind up with a CNR, combined CNR of 27.04 dB.
What's interesting, it's always so much worse than when I look at that and I see 31, 31, 30, I think 4 and 35, in my head, I was like, it's going to be slightly worse than the lowest number. But when you do that math and you add it up, it's always so much worse than I actually would kind of eyeball that number to be, because it comes out at 27. And I say, but how does it get that much worse when we add those together?
let's take a look at these numbers. We've got 32 and 32. So you combine those two carrier to noise ratios, and
that's
the CNR is going to be 3 dB worse.
Yep.
So already you're at 29 just combining those two upstreams alone. If you look at 34 and 35, they're almost the same. So you're going to at least be a little less than 3 dB worse here. So you see that you start combining these numbers and say, the combined CNR really is going to be worse than your lowest value. So in this case, it's 27 dB. And that would probably be good justification to go back to management and say, we got to get away from this
combining these nodes is bad.
These nodes and do dedicated upstream ports on the CMTS to each upstream optical receiver. And that's really why the cable industry did that, to get away from that additive noise like that.
And I think that's the important part. That's why I said even I do that when I look at it and I think, it's the overall, the average, because I think just mentally you have a tendency to average things in your head. But when you apply the formula, you realize how quickly they're not averaged. They're logarithmically summed together, and that drops quickly. As you said, just that 3 dB degradation takes a very quick hit, and dropping from like a 31 or a 32 to a 27 dB could mean the difference as to whether or not you can support 64 QAM in the return or cannot support 64 QAM in the return.
Yep, that's a great point. Now, I won't read through this definition. I'm just carrying this forward from earlier in the slide deck just to have it here so you understand what carrier to noise ratio is. So we look at our graphic here and we can see that we've got a carrier level of 27 dBmV and a noise level of minus 14 dBmV. So that gives us an apparent carrier to noise ratio of 41 dB. So we're basically subtracting where it's basically the difference between 27 dBmV and minus 14 dBmV. There are some things you need to take into account. As we discussed earlier, that noise floor measurement might have to be corrected to a specified bandwidth. If you're doing a carrier to noise ratio measurement for um, analog NTSC TV channels, it's 4 megahertz. So let's assume that your spectrum analyzer measured the CNR that you see here on the left, and let's say the resolution bandwidth control, the RBW control on the analyzer was set to 300 kilohertz. Well, that's not going to give you a noise measurement in a 4 megahertz bandwidth. It's going to give you a noise measurement in a 300 kilohertz bandwidth. So we need to convert that noise measurement to an equivalent as if you had a 4 megahertz resolution bandwidth setting on your spectrum analyzer. So if we measured the noise at 300 kilohertz bandwidth and we need to correct to 4 megahertz, here's a formula for making that correction. So it's 10 times the logarithm of 4 million, that's the 4 megahertz bandwidth, divided by 300,000, which is the resolution bandwidth setting of the spectrum analyzer. And we do the math and we get 11 and a quarter dB. So you have to add 11 and a quarter dB correction factor to our 300 kilohertz RBW noise measurement, in this case minus 14 dBmV. So we've got to add 11 and a quarter dB to minus 14 dBmV, which gives us minus 2.75 dBmV corrected noise level measurement. Now the real CNR is not what you see here, 41. It's actually 29.75 dB. So
that's a big difference.
Yeah, that's a huge difference.
And this goes back, so at the beginning of the presentation when you were saying, hey, our CNR is 41 dB, but is it really? Yeah. This is where you're going into saying, there's actually more to just looking at the analyzer and measuring what that delta is. You have to do some additional math and calculations, which you just went over here, and that's really important to getting to the actual CNR.
Yeah, people forget about this. They're going to get some bogus numbers.
Yep.
And that takes me to the next part of this. Before you measure the CNR, make sure that the displayed noise floor on your spectrum analyzer is the cable system's noise floor, not the test equipment noise floor. How do you do that? Temporarily disconnect the RF input from the spectrum analyzer and watch the noise floor. If the noise floor doesn't move, you're looking at test equipment noise. That's not the system noise. So you're going to get a bogus CNR measurement. You want that noise floor to drop at least 10 dB.
Now, on the test equipment, there's some things you can do to reduce the test equipment noise floor, Ron, correct?
Oh, there is. Sometimes you can use a built-in preamplifier. You can change the resolution bandwidth setting, but the important point is you want at least a 10 dB drop. I like more. The more the merrier, but if you don't get a sufficient drop or that noise floor doesn't budge, find a hotter test point or use a preamp.
Yep.
So for SCQAM, carrier to noise ratio measurements, as mentioned earlier, you don't have to correct for the noise floor like you do with analog TV channels. Just make sure that test equipment is displaying the system noise floor, not the test equipment noise. So same thing, you just disconnect the RF input from the analyzer. Did the noise floor drop 10 dB or more? You're in good shape. If it didn't, find a hotter test point. Now, sometimes you may need to use an external preamp because you simply don't have a hotter test point. You may also need to use an external bandpass filter so that when you're turning down the attenuator on the analyzer to 0 and using this external preamp, you want to make sure you're not overloading the front end of the analyzer. So it's helpful in this case to use an external bandpass filter in conjunction with that external preamp if you need to. Understand that some spectrum analyzers may have a built-in preamplifier, so you don't need to use an external one. Just check to see if the instrument supports it. Some do and some don't. All right, now let's get back to those two examples from the beginning of the presentation. Are the displayed CNRs accurate? And I would ask the question, what do you think? And just to explain where these came from, I took these screenshots, and I think this was an old HP 8591C years ago on my subscriber drop. So this is at the end of the subscriber drop, connected directly to the spectrum analyzer. And you can see the analog TV channels that used to be in the system here. They're not anymore. It's all digital now. And then the SCQAM signal. So are these indicated or apparent CNRs accurate?
Well, no. You have to correct for your resolution bandwidth.
Well, that's one part of it. But the part that you can't tell from these pictures,
Oh, your analyzer noise
yeah,
floor. You got to do
that's
your
the
unplug
analyzer noise
test.
floor, because these are typical drop levels, which are pretty low.
Yeah.
And so you disconnect the RF input from the analyzer, and that noise floor doesn't move very much. So these are, first of all, we're seeing mostly test equipment noise floor here. So we've got to find a hotter test point or use a preamp. And also for the carrier to noise ratio for our analog TV channels, yeah, and as you point out, Brady, there it is. The RBW is 300 kilohertz. You can see that in the lower left here. That noise floor has not been corrected to 4 megahertz. So no, these are not accurate CNRs. So you can't look at this and say, yeah, that's it. That looks good. Actually, not so much. You've got to figure out, why are the CNRs lower? And well, because the answer is, first of all, that displayed noise floor is not the system noise floor. And then, of course, we got to do the bandwidth correction. All right. Now, there comes another issue related to signal amplitude. If you're measuring the CNR of really, really low-level signals, and here I'm talking about where the signal level of the RF signal you're trying to measure is fairly close to the noise floor. And this might be something that occurs if you're measuring satellite received carrier to noise ratio on, say, an IF test point on a satellite receiver in the head end. It's not unusual to see a low carrier to noise ratio, and where the signal is actually fairly close to the displayed noise floor, and maybe even it's the system noise floor, but maybe it's only within a few dB. Well, what that can do is affect the apparent amplitude of the signal, because the signal inside the analyzer is so close to the noise floor that you're actually measuring a combination of signal plus noise when you're measuring just the signal. Then, of course, you measure the noise, and you're measuring the noise floor. So if you've got low value CNR measurements, you need to apply what's called a noise near noise correction. That's described in the SCTE math document. Here's a graph from that, and to give you an example, let's say you measure a CNR of 5 dB. So there's 5 dB, the measured CNR. You go up to the curve and then go across, and it says 1.5 dB. That's what you have to subtract to obtain the true CNR. So if you measure a 5 dB CNR, and then you need to subtract 1.5 from it, so that says you're actually at 3.5 dB CNR, because you're so close to the noise floor when you're trying to measure this. So that's an important point to keep in mind when measuring very low carrier to noise ratios. All right, this is a question that comes up from time to time. Are carrier to noise ratio and MER, or RxMER, receive modulation error ratio, the same thing? And here you can see a screenshot from a piece of test equipment that shows the MER on this constellation, or RxMER, is a little over 33 dB. So does that mean that that number is equal to your carrier to noise ratio where you're measuring this channel? Short answer, nope, it's not. It's not. And this surprises a lot of people, because I hear people say, CNR and MER, they're the same thing. They're not. CNR is one of several things that affect the reported RxMER from a meter or from a set-top box or cable modem or whatever, because there's a bunch of stuff that contributes to the reported RxMER. And some of those things include transmitter and receiver phase noise, nonlinear distortion such as composite triple beat, composite second order, composite or common path distortion, and so on. And in an all digital system, those distortions look like noise. And then, of course, linear distortion such as microreflections, amplitude ripple, tilt, group delay distortion. What, of course, that means is you can have really good CNR, and if you got bad group delay, for instance, you can have really bad RxMER in channel ingress, laser clipping, and so on. All these things can affect the RxMER. So what that says is CNR is just one part of that equation. So another important point when you're looking at RxMER and CNR, RxMER can never be higher than CNR. It's always usually at least a couple dB lower than CNR. If your instrument says that your RxMER is higher than your CNR, then there's something going on inside your test equipment that's not right. In some cases, you can see that the RxMER can be way lower than the CNR. particularly if you've got um, nonlinear distortions present. But the CNR is good.
So CNR is important, but it doesn't paint the whole picture that
Oh, no,
we
no,
have to
no.
look at.
It doesn't. It's an important metric to understand, though.
Yeah, right. Absolutely. So we use CNR for. I mean, we don't discard CNR because we use it for basically setting up the plant, setting up amplifiers, right?
Oh, yeah. If you don't set up the amplifiers correctly, you use the wrong padding,
Yeah.
and with modern day amplifiers that have mid-stage plugins in addition to input plugins, you can get those things out of whack and really mess things up. The manufacturers spend a lot of lab time testing their products and qualifying them to make sure that they operate with the channel loading that you specify, and they'll say, this is why we recommend this type of padding in these devices. And if you get that too far out of whack, you may wonder why is the CNR or the distortion really bad in this amplifier? I think I've got the padding right. Well, you may not have the padding right. So you want to make sure that you have stuff set up correctly, because it can have a big impact on things like carrier to noise ratio.
Yeah. So I kind of see CNR as like the baseline to set everything up, and then you measure your RxMER to make sure there's no underlying conditions beyond CNR.
Well, and you want to make sure too that you don't go too far the other direction and cause the amplifier to generate too many distortions. I mean, all amplifiers generate distortions. That's a fact of life and part of good old-fashioned physics. But you want to keep them down to a dull roar, and that is also closely tied in with where you set the amplifier up with proper padding and equalization to ensure you've got good CNR and you have good carrier to distortion ratio. And the two, there's a lot of interaction between the two, and especially as you get into the world of all digital networks, those signals in the networks are like noise. And what happens is you get a combination of thermal noise, good old CNR, and digital distortions or noise-like distortions. And yes, they combine, and you'll get what looks like a really bad CNR when actually that noise floor you see is a combination of thermal noise and noise-like distortions. And you can think the CNR is bad, but it's actually not. It's not bad. What's bad is the carrier to distortion ratio, but you can't really tell just by looking at the analyzer display in a network that's all digital these days.
Right. Makes sense, Ron.
Yeah, and anyway, there's a lot more about what I've talked about thermal noise and carrier to noise ratio and so on. The SCTE math document is a great reference. That HP application note I mentioned earlier is a good reference. And then, of course, SMRP, as we call it, SCTE Measurement Recommended Practices for Cable Systems. This used to be the old NCTA Recommended Practices for Cable Systems, and SCTE took this over several years ago. It was just updated, is now available for download on SCTE's website. SCTE used to sell this document. It's now available for free. So this talks about how to do proof of performance tests and carrier to noise measurements and carrier to distortion measurements and so on. So good material. I would recommend both of these in your library. And with that, any questions?
Excellent recommendations, Ron. No more questions in the chat room so far. If any come in, we'll definitely address them. So I think that was a great overview on CNR, carrier to noise ratio.
Let me click stop sharing.
Yeah, thank you. So yeah, absolutely. So I think we covered the dB now. We've covered signal levels. We covered CNR. What's next, Ron, that we're going to cover?
Oh, I've got a few things in my mind. One, of course, is carrier to distortion ratio. I think that's an important one to talk about, particularly what I just touched on, or considering what I just touched on with these so-called digital distortions or noise-like distortions that occur in a cable network that's carrying mostly or all digital loading. There's another one I've got in mind and I'm trying to decide, do I do the distortion one first, or do I do one on what is RF?
Another good topic. So definitely for those of you listening, drop us a note in the chat or drop a comment below if there's particular topics you want us to focus on, and we will definitely talk on those. Peter, dropping some more comments in. Thanks, Peter. Says, a question?
He has a question.
He says, I'm sure it's clear, but just to mention it, that the view on the CNR added by the amplifiers are also important for our upstream amplifiers to design and plan the network.
Yes, that's a great point. And when we go back to that example of combining upstreams, upstream CNRs. We want to make sure we design our network so that we have decent CNR, because it's one thing to think of calculating a cascade of amplifiers, the CNR at the end of that, but in the upstream, it's all the amplifiers, not just what's in the number in cascade. It's all the amplifiers that are combined together because of good old reverse funneling. So that can get messy too. And yes, you need to take that into account. CNR is such an important metric to understand for proper operation of our cable networks.
And Peter goes on and he says, and to keep a good CNR at the CMTS, the question to me, is there a chance that the CNR for the downstream and upstream path at the same amplifier are different because of different signal paths inside the amplifier and different parts for upstream or downstream and upstream, especially also with new DOCSIS 3.1 high split, where you have to select new amplifiers?
Well, I think the answer is it depends, but bottom line is yes, you can have very different CNRs in your upstream and your downstream. That's a fact of life, and unfortunately, in the upstream, where it's that 10 log n, where n is the total number of amplifiers in the return path in a given node service area. In the downstream, we calculate CNR based on the cascade of amplifiers, one after the other. It's a lot different than the way we calculate it in the upstream. So yes, it's not unusual to see the upstream CNR quite a bit lower than what you see in the downstream CNR in the same node service area. That's not unusual at all. So you really need to understand CNR, how to set up the forward amps and the return amps to make sure you have optimized network performance given your architecture and the type of equipment you've got.
Yeah, traditionally, we've set up the forward and return with plug-in pads and plug-in equalizers. A lot of the new amplifiers that are coming out now don't have plug-in pads and equalizers. They have automatic pads and equalizers that you tune with maybe an app or even remotely. They're adjusted. So I think these are going to add new I don't know that they're challenges. I don't want to use that word, but new ways that we balance our amplifiers and maybe interesting opportunities for the way CNR is managed within our networks, because we'll be able to maybe, we talk about smart amplifiers, so we'll be able to remotely measure CNR, and there's also work that we're doing within, you're well familiar with, Ron, within the Cable Labs P&M working group, where we can detect poor CNR through full band capture, so it's through like distortion, and so having visibility to this will give us the ability to not only detect it, but maybe automatically with these new amplifiers go out and correct it when we see CNR issues out in the field. So lots of interesting stuff. I mean, Ron, well, you, me more so than I, but myself, been out in the industry for such a long time, and it continues to change and continues to get really exciting. So Matthias says, hi all, brutal amateur here, diving into the deep and the multiplication, lost my place here, factors of multiple noise sources remains constant over so he's saying diving into the deep end, the multiplication factors of multiple noise sources remains constant over frequency and indefinitely. And these are questions I think he's asking. So I think, there's definitely lots of different noise sources over there. I think his question is, are they constant over frequency and are they constant indefinitely?
When we calculate carrier to noise ratio in the downstream, the general assumption is that the thermal noise is going to be constant over frequency. And if you look at a noise figure plot for an amplifier, for example, it's reasonably flat over the operating frequency. Likewise, the gain of the amplifier, reasonably flat over frequency. So we could, if we're doing a carrier to thermal noise ratio calculation, the assumption is that the noise is more or less uniform over frequency. Now, in the real world, you can have other things that get in the way, ingress and so on. If your amplifiers are misaligned and you start getting noise-like distortions building up, those may not be the same amplitude across frequency. And you can think you've got a carrier to noise ratio problem when it's a carrier to noise plus noise-like distortion problem, and that may not be uniform with frequency. Of course, the upstream, same general rule applies, but we've got all this ingress and burst noise and other stuff that gets into the plant that can really mess things up and make it much more difficult to manage the carrier to junk ratio.
Yeah, I was wondering what word you were going to come up there. It's
Yes.
garbage. It's just junk noise. It's totally
Yeah.
correct. And then the carcinator. Also, the downstream has higher modulation than the upstream, which means noise is going to have potentially a greater impact on the downstream than it is on the upstream. But the upstream typically has a lot more noise than the downstream.
Yes, it does. And it's true. You can generally get away with, say, 4K QAM in the downstream with OFDM. Upstream, maybe you can do 1K QAM, maybe 256 QAM. Depends on what your noise situation looks like. But hopefully, attendees and viewers have taken away from this presentation that there's a lot of math involved in carrier to noise ratio and understanding it, but an understanding of it can help you to appreciate the importance of being able to calculate the CNR. And then if you're out doing troubleshooting or maintenance, you can say, all right, for this 5 amp cascade after the node, the calculation says this number, and what am I measuring? I'm within a dB or two of that. Things are probably pretty good. If you're 5-6 dB off, you better go back and find out what's going on.
Yeah. All right, Ron, we are at the top of the hour. Thank you so much. This was a wealth of information. I think CNR is a bit more complicated than it looks on the surface. So, folks, for everyone watching, really hope you enjoyed this information that Ron's provided on CSR or CNR. CSR, totally different topic. Don't forget to subscribe to our channel and so you get notified when we're coming up with the next show and next content. Don't forget to hit the notification bell and subscribe. We sure appreciate, just push all those buttons down there. Our next episode is next Friday, May 19th at 2 p.m. Eastern Daylight Time. John Downey and I will be back. We're going to be covering the topic of return path monitoring using something called Upstream Triggered Spectrum Capture, or UTSC. So be sure to check in. And Ron and I will hopefully be back soon talking about one of the topics that he's working on for our next show.
It'll be one of those two. I just need to decide which one I want to do and in which order.
We'll be looking forward to it, Ron. So, Ron, thanks again so much. This is great information. We look forward to having you back soon. Until next week.
My pleasure, Brady. Thanks for having me here. It's fun to be part of this.
Awesome. Take care, all. So long.